In this video, welcome to Crazy Physics again, and this is just an excerpt for electric circuits. And in this video, we will just quickly look at the voltmeter. This is a very important device when we talk about electric circuits. We need to understand how it works and the properties for us to be able to really understand the dynamics of current. All right, so let's talk about a voltmeter quickly. A voltmeter. Now, what is a voltmeter in its real sense? All right, so a voltmeter. I'm just gonna quickly change my pen. All right, a voltmeter. Now, a voltmeter is a high resistance device that measures the potential difference. We're going to break this down just now. Across 2 points. All right, when we say it measures potential difference, what do we mean? Potential difference V. V is the work done per unit charge. All right, so what is potential difference? It's the work done, and when we talk about work done, we talk about energy measured in joules. All right, to move a charge from one point to another, or rather to move one coulomb of charge, we need to put that there. To move a coulomb of charge, a coulomb C, all right, of charge from one point to another. Now, when I say the word move, I'm referring to the flow of what? Charges. And this we know is current. All right. So, the voltmeter is therefore a device that measures. I'm going to change or elaborate more here. It measures the energy per coulomb. It measures the energy per coulomb used across 2 points. I'll explain. Across 2 points. Let's draw a circuit quickly and try to make more sense out of this. All right, so if I have a circuit here, and let me look for straight lines so that I can have something more perfect, just a very simple circuit. All right. Okay. All right. Just a very simple circuit. Okay, I need to have all right, I'm going to just put a box here so that I have my lovely. I have that. Okay, now number one, a voltmeter must be connected across, okay, in parallel. Okay, I want to connect a voltmeter here, V1. I want to connect another voltmeter here, V2. All right, so Number one, we said a voltmeter is of high resistance voltmeter. It's a high resistance device, which means it must be connected in parallel across the point. All right, because if we connect it in series, then it will not allow current to flow because of the high resistance. All right, so if connected in series, blocks the flow of charges because of its very high what? Resistance. And remember, resistance and current are inversely proportional. So if this is very high, automatically we're going to have very low, and if it's extremely high, then we probably have no current flowing. There's just a little current flowing, very little. All right. Okay, so if we have a positive and a negative, we have a positive and negative terminals. All right, we know that if we then have the movement of electrons, I want us to see how a voltmeter really works. All right, so we have an electron here, okay, which moves this way. All right, negative and positive. Now current moves that way, rather. Okay, current moves this way. Okay, but an electron will rather move this way. All right, an electron moves that way, but conventional current moves from positive to negative. Remember, there's a negative terminal, so there is a repulsion. But current moves the other way. Okay, that's a discussion for another day. Now, when this electron leaves the cell, what happens? It leaves full of energy, because that's what the cell does. It gives it energy. Now, when it comes through here, it is going to do some work here. All right. Now, it is so full of energy. Let me use a full bar of energy here. It is so full of energy when it gets in here. But when it goes through this resistor, what happens? It does work. Now, if anything is doing work, what happens to the energy? The energy is lost. All right. So, full energy here. But when it does work here, we are going to have, this is the same electron, but let's have this level of energy because work has been done. All right. Work has been done. Oh, by the way, I need to have closed this. Let's have this closed. Beautiful. Let's have that closed. Okay. Now, what your voltmeter does is to measure the difference. So this is the initial energy. All right, and this is your final energy. So what your voltmeter does is to measure the, remember we call it the potential, electrical potential energy difference. Because when we talk about potential, so it's potential energy difference. All right, which would be the difference between your E final minus what? E initial, but it's not going to be negative this time around. All right. Remember, energy is a scalar quantity. Okay, energy is a scalar quantity. If we get a negative here, just telling us we're losing energy. So your potential energy difference. Okay, I wrote the word difference, and this is what your voltmeter measures. So it's energy per coulomb, and that's volts. All right, so if it goes in here, for example, let's say it goes in here with 10 volts or 10 joules, all right, 10 joules, and comes out here with 8 joules. What's the difference? It's going to be 2. So your voltmeter is actually reading 2 joules per coulomb, and that's why we have it as 2 volts. All right, and as we go on, what happens? This is why we call it up. When they are connected in series, we call it potential dividers. Okay, let me try to put a voltmeter here, another resistor here quickly, and we have it as V3. So check this. Depending on the resistance, the level of work that will be done. So this 8 joules comes in here. All right, depending on the level of resistance that we have. Okay, now it is going to come out of here as well. All right, now let me do something a bit clearer. Let's move this. Okay, just to create better concept. We said this is our V2. Okay, now so remember the 8 joules comes in here and comes out here. I need a circle first. All right, again the energy has decreased. All right, the energy has decreased based on the value of the work that it's going to do. So let's have this as 4 joules coming out. So what's the voltmeter reading here? It is 4 joules per coulomb. How did you get the 4? It is the 8 minus 4, or the 4 minus 8, but it's losing. All right, so we can have 4 minus 8. All right, negative 4. The negative simply tells you that energy is used, but your voltmeter reading is just going to be 4. Okay, but negative on the calculation tells us that it is used joules per coulomb. Remember, it is a scalar quantity. All right, now do you see that potential difference is divided because it gets used, and as it goes, what happens? It's going to go through this wire now, or the switch. All right, your switch is actually of no resistance. All right, very, very low, approximately 0. Now your 4 joules that is remaining was going to go through as 4 joules because no work is done. All right, so it comes here as 4 joules. So what's the difference? It goes in at 4, comes out at 4. The voltmeter reading here would be 0 volts because no work is done within the switch. It's of low resistance, absolutely, we call it negligible resistance. Now the 4 joules, then the electron then goes and gets recharged here. It gets recharged and then goes around the circle again. So that's the flow of electrons. But remember, current would move conventionally from the positive to the negative. All right, so this is what your voltmeter does. It measures the difference in energy. So it's trying to calculate the energy used. All right, so your voltmeter measures the energy used per coulomb. Measures the energy used per coulomb. Energy used per coulomb. I hope that makes sense. So we have 10 there, 8 there. My reading here is 2. 8 here, 4 here. My reading here is 4. 4 here, 4 here. My reading here is 0. So basically, that's how your voltmeter works there. All right, let's quickly look at a question, a very interesting question here. I have this question. It says the circuit below shows a 12-volt battery of negligible internal resistance connected to a combination of 3 resistors and a rheostat. Okay, a rheostat is a variable resistor. You know, if you check some of our videos, you have a variable resistor explained there. The resistance of the rheostat is 5. Explain the term ohmic conductor. All right, ohmic conductor is a conductor that obeys Ohm's law. All right, a conductor that obeys Ohm's law. And this is the graph of an ohmic conductor, V and I. And if I were to have this, then I'll call this a non-ohmic conductor. All right. 8.2. Calculate the total resistance of the circuit. All right. If you notice here now, let me try to Okay, conventional current would move this way, move this way, move this way. It splits there. All right. So if it splits, it means these are connected in parallel. However, these are connected in series. So we have two sets of series that are connected in parallel. So I will then call it series 1 and series 2. All right. So how do I calculate series 1? All right. I have R1 plus R2. However, I like to use the value of the resistors. All right, so this gives me 20 plus 30, and that gives me 50 ohms. But R series 2 would be R10 plus R5, which is what? 10 plus 5, and that is 15 ohms. But both of them are connected in parallel. All right, product over sum. So I'll say RS1 multiplied by RS2 over RS1 plus RS2. And that will be 15 times 50 over 15 plus 50. What will that give us? Let's quickly get a calculator here. So we have 15 times 50 and 15 plus 50. 11,54. All right, beautiful. 11,54 ohms. Done. All right. 8.3. Calculate the current through the battery. I'm just going to clone my page. All right. Calculate the current that flows through the battery. Now, since we're talking about current that flows through the battery, it means we're talking about the total current. And when I use total current, I'm going to use total voltage as well. So I know that V total equals to I total multiplied by the R total, which is 12 equals to I total times 11, what? 54. If we then divide both sides, our I total will be, get a calculator again quickly, 12 divided by 11,54, and that will give us a 1,04. All right, 1,04 amps. Very key. Beautiful. Now, a high resistance voltmeter is used to measure the potential difference between points B, F, A, and C in turns. Okay, let me clean this that I wrote here so we can have a clear diagram. Beautiful. Write down the voltmeter reading between B and F. So we have 8.4.1. Now, what you would notice here is these things are connected in parallel. So if I have an acronym that I like. South African Police Department is paid. Series are potential dividers, parallel are current dividers. All right, so these things are connected in parallel, so let's focus here. So we have AB. The question says between B and F. Oh, so you have a voltmeter connected this way between B and F. All right, now because this and this are connected, so if I have another voltmeter here, all right, they're connected in parallel. Parallel are current dividers, so potential difference remains what? The same. Is the same. So basically, it is 12 volts. It's going to be 12 volts here, and it's also going to be 12 volts there. All right, so that's why the examiner even told us to write down 12 volts. All right, 8.4.2. Calculate the potential difference between A and C. Okay, I'm going to need to clean my, let me just clone so that I have it on a fresh page. Between A and C. Sounds like a political party there. All right. But this is not politics, this is electricity. All right. Between A and C. I'm going to clean this one here. And then draw a fresh one. A and C. Lovely. Now understand that because these guys are connected in series, like we said, potential difference will be divided. All right, so between A and C, I already know that it's 12 volts across that path. All right, but I need to get the potential difference. How am I going to get the potential? Because it is divided. First, I would need to calculate, just need to calculate current first. Okay. So if I have 50, or you can use your ratios, all right, because current there will be the same. All right. Let me first work out the whole calculation, then use ratios as well. My R in series 1 is 50 ohms. All right. So V equals to what? IR. All right. We do know the total potential difference there as 12. And my current, I don't know, and the resistance is 50. So I will be 12 over what? 50. Now, but the current flowing through the 20 and 30 are the same. So V across AC would be I multiplied by R, which is 12 over 50. All right, this is just going the long way, but it's just to make everyone appreciate the basic dynamics of electricity. Even a grade 10 learner would be able to understand that. All right, 12 over 50, remember that's the current multiplied by 20, which is the resistance. And that gives us 4,8 volts. Beautiful. 4,8 volts. All right. An alternative way is, since we know that current is the same, all right, since current is the same, we can then divide the potential difference 12 volts in the ratio 20 to 30. Okay, 20 to 30. So we're looking for AC. This is AC and this is what? CE. Because current is the same, we can divide that. So how do you divide? It's going to be 20 over the total ratio 50, all right, times 12. You would see 20 over 50 times 12. That is working with your ratios. You have 4,8 what? Volts. All right. So we divide 12 volts in the ratio 2 to 3. That will give us 4,8. Okay, beautiful. Now, calculate the potential difference across C and D. I'm going to clone this page and extend this question a little bit. Okay, and rather I want to do something here. Just a second. Let me do all my good. I just want to clone this and have a very big diagram. There I go. Yes, this is what I want. All right. Now, remember that already we have a voltmeter reading here. Okay, and I'm going to have another voltmeter reading here. So let's call this V1, V2. We can also, to buttress understanding, create V3 here, all right, and also create V4. But don't forget the dynamics, that V1 plus V2 will be equal to 12 volts. V3 plus V4 would also be what? 12 volts. Is that okay? All right, because they're connected in series. We did get this one as 4,8 volts. Automatically, this one would be 12 minus 4,8, and this would be 7,2 volts. I hope that makes sense. All right. In the same way, we can actually calculate what's going to be on V3. Again, if I use my ratio, because it's 12 volts, we want to divide 12 volts in the ratio 10 to 5. So what am I going to have between B and D? So BD here and DF here. All right, so 10 over 15 multiplied by 12. And what will this give me? 120 over 4 over 15, that will be 8. Okay, Let's use a calculator to confirm, but that should give me 8. Let's just confirm that quickly. 10 times 12 divided by 15, 8 volts. Lovely, 8 volts. Okay, so if I then have 8 volt here, I'm going to have 4 volt here. I hope that makes sense. Now, the examiner says we want to measure potential difference across CD. Very unusual. So we have a V5 there. Good. Now, let's see. Positive and what? Negative. So your electron, remember that's your charge, goes this way. Comes this way. Comes this way. Alright, goes that way. So it is the same charge. Okay, so it is the same electron. And this electron actually has 12 joules per coulomb. 12 joules. It has not done any work. So they are identical electrons. That's why when we say parallel connections have the same potential difference, this is it. Alright, so all the electrons coming out of this battery have 12 joules per coulomb. So when it gets there, one goes this way, the other one comes down this way. So that's why the joules per coulomb in parallel connections remain the same. Now, when this gets here, it's 12 joules. Is that okay? By the time it comes out here, we have extracted 4,8. So the remaining is 7,2. So we've extracted. So at this point, this charge no longer has 12 volts. This charge has 7,2 volts. That is the charge that it's going to take through to this point. Alright? And at this point, it's actually going to have 0 because it will have exhausted and then it comes again to recharge. I hope that makes sense. Alright, so when it goes in here, it has 12. When it comes out here, it has 7,2, which the difference is 4,8, potential difference. The same way, the 12 goes in here, alright. When it comes out here, it has 4 volts. Why? We have taken away 8 volts. Okay, so between here and here, we talk about potential difference. Potential difference. What is the potential difference between 4,2 and between C and D? Remember, how did we get our 4,8? 12 joules per coulomb minus 7,2. It went in here with 12, came out with 7,2. That's how we got our 4,8. It went in here with 12, came out with 4. That's how we got our 8. Oh, so if it is going in here now, let me use a different color now. If it is going in here and coming out here, because we're creating a connection, the voltmeter. Alright, we're measuring the potential difference here, the difference between the two. Again, this voltmeter measures the potential difference between there and there. Alright, potential difference. So this one as well will measure the potential difference between this point and that point. And what will that be? 7,2 minus 4, and that will be 3,8 volts. I hope it makes sense. Alright, even if we were to change the terminal and put the negative terminal here and electrons go this way, I hope you understand. I've changed the terminals. Alright, the electron going here has 12 joules per coulomb. Again, the other electron, identical electron, has 12 joules per coulomb. But when it comes out here, if we have 7,2, or let me just create a different page here. Let me clone this page and create a different page for you for clearer understanding. Okay, let's clean this again. I'm deciding to change the terminal just for us to be able to see. Oh, I shouldn't have cleaned everything, but it's fine. Beautiful. I'm just going to clean, which one am I going to clean? Here. Yes, I want to clean this one. Remember the answer we got? 3,8. Follow the red now. Follow the red. So, I have 12 joules per coulomb and 12 joules per coulomb. So when it gets here, it's 12 joules. All right. When it comes out of here, it's actually going to be 4,8 because we are using 7,2. So when it gets here, it is 4,8 volts. So the 12 minus 4,8 gives me the 7,2. Oh, the same story here, the 12 minus the 4. So here it is 8 volts. Is that okay? 8 joules per coulomb. If you want to use that language, 8 joules per coulomb. All right. So between here and here again, what is the potential difference? 8 minus 4,8, and that will also give you what? 3,2 volts. I hope it makes sense. All right, so that's how your voltmeter works. It measures the potential difference, the joules per coulomb, the energy to move an electron across 2 points, joules per coulomb. So it's 3,2. All right, so if I were to write this down, how would I then write it down? I would first say, let me do something here. Let me crop this question. Let me just crop this question so that I have the question in view. I just want to have the question in view. Okay, and I'll take it down. There we go. All right. So I want to answer 8.4.3 now. 8.4.3. All right. So I need to calculate the potential difference across BD. All right. I need to calculate that, and we can use our ratio like we did. Is that okay? Or you can use your normal formula. So if I want to use my ratios, I want to divide 12 in the ratio of what? 10 to 5. All right, so it's going to be, so V in BD will be 10 over 15 multiplied by 12, and that is your 8 volts. Or if you don't want to do that, we can first calculate current. All right, current in BF across that whole path. VBF equals to IBF multiplied by RBF. So 12 equals to I, and this is 15. So my I is 12 over 15 amps. Now the voltage in BD, since it's the same current, which is IR, will therefore be 12 over 15. That's my current, and my resistance is 10. All right, so you would see I'm back there, which is what? 8 volts. All right, so now the V across CD will therefore be 8 volts. It will be VBD minus VAC, which is 8 volt. 8 volt minus 4,8 volt, and that will give us 3,2 volts. All right, I hope that would really have helped. Okay, now 8.5, the rheostat is adjusted so that its resistance increases. How will this adjustment influence the voltmeter? All right, now look, we are not changing the battery. All right, we're not changing the battery, so the battery is still 12 volts. So my answer would be 8.5 stays the same. Explain. All right, an increase in the value of the rheostat in the total resistance does not affect the EMF of the same battery. The same. So battery is unchanged, which means the battery is still going to have the same energy. All right, what changes would be current, but how electrons flow, but the battery would have the same value. Let's quickly try to do something here and use a simple simulation to work something out quickly. All right, I tried to recreate the whole, yes, I tried to recreate. If you remember, we have a 12 volts with no internal resistance. I have a 20, I have a 30, I have a 10, and then I have a 5. If I measure the potential difference here, let's measure. Remember, it was A, B, C, D, E, F. The first question was 12 volt. Awesome. And if I take that voltmeter here and measure here, 12 volts as well. Beautiful stuff. Now, if I measure here, remember we got 4,8. Hopefully, let's see. Oh, that's 4,8. And I remember here we got 7,2. Is that beautiful? Now, remember here we got 8 volts. Oh, beautiful. And here, remember we got 4 volts. Awesome. Now, if we measure between C and D, that's our 3,2 volts. Beautiful. Beautiful stuff. Beautiful. 3,2. Okay. Now, we've done all the explanation. That is 12 volts. I want to change this, the value of this resistance, of this rheostat. Change resistance, and let's make it 10. Let's see. Will that affect? Let's see. Did it change? Yes, 10. Oh, but it's still 12 volts because we're not changing the cell. We're using the same cell. So it remains as 12 volts. All right. I hope this then helps us to understand how a voltmeter works. All right. Thank you. We'll get to see more questions and see how to maneuver around this type of questions. But this is a very lovely concept, the concept of the voltmeter reading. Goodbye.